All right, our second video here is going to be about finding the length of a vector, kind of tracking that back to the unit vector, and then also how we figure out the distance between two vectors. One of the formulas in this notes packet that I did not copy here that I want to make sure that we know is that you find length. And another way that we call this length is the norm of a vector v, and that's the notation, okay? By squaring all of the pieces of v, like all of the components of v, and then taking the square root of that. So it's kind of like the Pythagorean theorem, if you will. So that's how we're going to find the length. Now, a vector whose length is 1, we're going to call that a unit vector. So it says here, if we divide a non-zero vector by its length, so we take 1 and we divide by the norm, then we will obtain the unit vector u because it's going to end up having a length of 1. So we also call this normalizing v, or we say that u is in the same direction as v. So let's look at an example here. So I have v, find a unit vector u in the same direction as v. So the first thing we're going to do is find the norm of v. And so that's the square root of 1 squared plus negative 2 squared plus 2 squared plus 0 squared. And that ends up giving me the square root of 9, which is 3. And so u must be 1 over that norm times my vector v, because it needs to be in that same direction. So I'm going to take 1/3 and multiply it through by vector v. So that's going to give me, maybe I write it in R4 here. So it's going to give me 1/3, negative 2/3, 2/3, and 0. And you can double check and make sure that that has a length of 1. It does. You end up getting a 9th plus 4/9 plus 4/9, which gives you 9/9. And then when you take the square root of that, you get 1. All right, let's look at another example. Let W be the subspace of R2 spanned by this x vector. So let's write that in a vector notation. Find the unit vector z that is a basis for W. So if it's a basis, then and this is a subspace, then W must be the span, right? It must be all multiples of x. And so any non-zero vector that's in W is going to have to be a basis for that. So if we want to simply scale x, we could multiply it by 3 just to make it nicer, right? And then let's go ahead and normalize that. This might be a little bit nicer to find the norm of. So we end up getting 4 plus 9, so square root of 13. And so a unit vector z in that basis would be 2 over root 13 and then 3 over root 13. All right, now let's talk about distance. So the formula for distance is as follows. The distance between u and v is the norm of u minus v. And I want to show you with a graphic here why that's the case, specifically for these unit vectors, but just in general. So if I need to figure out the distance between vector u over here and vector v, that's going to be like this line, right? Well, that's u minus v. So it makes sense that I can just take the distance of that difference, and that's going to be the distance of the vectors. Okay, so we need to find u minus v first. And that ends up being 4, -1, which makes sense. There's u minus v right there. Okay, 4, -1. And so if I need to figure out the norm of that, that's going to be the square root of 4 squared, 16, plus 1 squared, 1. So that's going to be the square root of 17. So that must be the distance between those two vectors. Okay, you can also think of it like, I mean, it's the Pythagorean theorem, right? Like that's basically what we're doing here, or the distance formula in R2. So let's expand this into R3. Okay, so if this was in R3, then the distance between u and v, the norm of that, you are going to be looking at the distance between each and every one of these pieces. So u1 minus v1, u2 minus v2, u3 minus v3, each one of those. And we would do that anyway, right? Like you would have u1, u2, u3, you would subtract out v1, v2, v3, and then you would need to take those differences that you find in that vector and then plug them into the formula. So that's how you expand this into 3 space or beyond.